Good morning. As we get into this next section called properties of logarithms, it's good for us to keep in mind that when we have exponential equations, we solve them using logarithms. Here's a quick example. 10 to what power equals 407? Convert over to log form. That would be x, the exponent, equals the log base 10 of 407. That's the common log. Grab a calculator, and you'll see that that comes out to about 2.6. And if we have log equations, like the natural log of x equals 9, or that means the log base e of x equals 9, we can convert that over into exponential form. E to the 9th equals x. Again, grab a calculator, and we can solve that. So when we're dealing with exponents and logarithms, we understand that they're inverse operations. We switch their positions, and then it helps us to understand how when we get into properties, the properties of logarithms are going to be based off of the properties of exponentials. So something that graphs exponentially, if we convert over into logarithms, we can see how that would switch. And maybe even better, put them together, see how one is a reflection of the other over that line y equals x. If you can keep that basic thought in mind, it'll help us as we get into our properties coming up. In this lesson, we're going to discuss 3 properties of logarithms and also a change of base formula. To begin with, keep this essential question in mind. How do the properties of exponents help us derive the properties of logarithms? It helps if we remind ourselves how to translate, how to convert from logarithmic to exponential form. Our bases are always the same, and logs are equal to exponents. So to take our first expression, that log base b means we're going to have b as our base, x as our exponent, and it equals m. And similarly, to the right, we should have b to the y equals n. In exploration 1, we would like to multiply m times n together. That's equivalent to b to the x times b to the y. And when we multiply with the same base, we add exponents, so that should give us b to the x plus y. If we take that concept of that property with exponents, we then come to the log base b of the product of mn, and that can expand through addition. Pause here to see if you can determine how that's going to look. The log base b of m times n can be expanded into the log base b of m plus the log base b of n. That's 2 log expressions added together. That's equivalent to adding exponents together. When do we add exponents? When we're multiplying with the same base. You notice back in that log expression, the m and the n were multiplied together. That's the product property of logarithms. If we were just reminded that when we multiply the same base, we add exponents, so b to the x times b to the y equals b to the x plus y, when we divide, we would subtract. So you can see in exploration 2, b to the x divided by b to the y is equivalent to b to the x minus y. We've done this before. But now how do we take that information and translate it into logarithms? If we say the log base b of the quotient m over n, that can separate into, or we would say expand, into x minus y as it's written here. But how would we write that as 2 different log expressions? Pause here to think about and write down your own answer. We would come up with the log base b of m minus the log base b of n. And it might make some sense here to just pause and think also about this. We are going from left to right. The log base b of m over n is equal to that expanded version. But we can also go from blue to black, from right to left. If we have 2 log expressions with the same base and they are being subtracted from one another, we can condense that, we can bring them together through division. Our third property today is going to be the power property of logs. And so remember, there's also the power of the power property of exponents. Let's look at a quick example just to remind ourselves. When we take x to the 4th and raise that to the 6th power, that can be simplified by multiplying those exponents together. 4 times 6 leads us to x to the 24th. So if we want to take in exploration 3 the log base b of m raised to the nth power, it's suggested to us to make a substitution. Switch out the m and replace it with b raised to the x power. When we do that, we'll have the log base b of b to the x raised to the nth. Again, you can see the similarity here between x to the 4th raised to the 6th and now b to the x raised to the nth. We can bring those together as the log base b of b raised to the n times x. And the inverse property of logs tells us that the log base b of b raised to some exponent simplifies down to that exponent. So we're just simply left with n times x. So if we substitute the log base b of m for x, we'd have the log base b of m raised to the nth. That can give us n times the log base b of m. That's the power property of logarithms. Here are our core concepts for today for the properties of logarithms. We have the product property, the quotient property, and the power property. They're on your class notes, they're on the slide. It might be worth your while to write these down. And keep in mind also that these come directly from our properties of exponents. Our first example today is sort of just an academic exercise because we have calculators at our disposal. We don't need to go to this length to find out our solutions, but it is good to recognize that these properties work using these approximations. So in example A, we want to evaluate what's the value of log base 2 of 3 divided by 7. As soon as we say 3 divided by 7, do you see that the quotient property is going to come into play? We can separate that through subtraction and say that's the log of base 2 of 3 minus the log base 2 of 7. And take a look up in our directions here. They give us those approximations. Write them down, perform the operation, and we come to our approximate answer. In example B, when we see the log base 2 of 21, I don't immediately see a property at play, but when I see that we have the log base 2 of 3 and the log base 2 of 7, I recognize that 21 is 3 times 7. That multiplication tells me that we can use the product property here. We can separate into two log expressions through addition, and if we know what the log base 2 of 3 and the log base 2 of 7 are approximately equal to, we can add. And finally, what's the log base 2 of 49? Well, we can only deal here so far with the log base 2 of 3 and the log base 2 of 7. Oh, I recognize that 7 squared equals 49. So we can express that, and as soon as we see that exponent, take a look at how the power property plays out. We don't necessarily know what the log base 2 of 49 is, but if we take that 2 of the exponent and bring it out as a coefficient, then we can say that it's 2 times that log base 2 of 7 approximate value, multiply, and we'll come to our answer. We'll find out real soon that the calculators can get us to these answers a little bit more quickly, but it's good to see how these properties work. The study tip in the top right corner is worth mentioning. When we're expanding and condensing logs, our variables are positive. So if we work to expand this natural log, there's a whole bunch of information there. It's the natural log of 8x to the 4th, all divided by the square root of. There's a lot of information there. Just setting up those parentheses helps me to zero in on what it is that we're going to expand. And also, if the power property is going to be in play, I want to convert the square root into raising something to the 1/2 power. Now, I'd like to take the numerator and denominator and separate those through subtraction. That's the quotient property. I'd like to take that 1/2 and bring that out as a coefficient. That's the power property. And inside both of those parentheses, the 8 and the x to the 4th is together with a multiplication. Similarly, it's 5 times y cubed. We can expand multiplication by rewriting it as addition. And then we can also now take a look inside and recognize that we have x to the fourth and we have y cubed. So the power property brings both of those down as coefficients. And this is a perfectly acceptable way to write this. It is also possible to just distribute that 1/2 so that we would have finally the natural log of 8 plus 4 times the natural log of x minus 1/2 the natural log of 5 minus 3/2 the natural log of y. Now we're going to reverse directions and condense logs. Keep in mind how exponentials work. If we want to multiply x cubed and x to the 8th, we're allowed to do that because the bases are the same. We add the exponents, we come to x to the 11th. When we're going to try to condense, we need to have the same bases. In the example we're going to work on in a moment, there are common logs base 10. We don't see the 10, but in this example that's showing now, the log base 10 of x plus the log base 10 of x can come together as the log base 10 of x squared, x times x or x squared. Can't that also have that 2 come down as 2 times the log base 10 of x? And wouldn't that make sense? Log base 10 of x plus itself equals 2 of them. Let's keep that in mind as we get into our next set of problems here. We're going to condense these, so let's deal with our coefficients first. Using the power property, the 3 can go up as a cube and the 1/2 can go up also as an exponent. Now, it's easy enough to figure out what 4 cubed equals, and if it looks a little bit nicer to you, we can switch that x to the 1/2 power as being the square root. So now it's a little bit easier to bring these together. The first two expressions are separated by addition. We can merge them through the product property, making it a single log of 64 and the square root of x. We can also take that minus the log of 8 and bring that into the quotient of the log of the numerator 64 times the square root of x, all divided by 8. And we can even simplify that. 64 over 8 just simplifies down to 8, and so we have our. Another key concept for us in this section is called the change of base formula. So far we've learned how to solve log equations with log base 10 or log base e, that's the common log or the natural log, but what if we have something that's log base 3 or log base 7? What can we do with that? Well, provided that a, b, and c are all positive numbers and b is not equal to 1 nor is c, we can take the log base c of a and rewrite it as the log base b of a divided by the log base b of c. What is b? B is whatever makes sense. In certain situations, we may want to change the base so that it's going to simplify more easily with either a or c, or we can simply switch that over to the log base 10 or the log base e. We can go to the common or the natural log. So let's look at some specific examples here. We want to evaluate the log base 6 of 31. We're asking ourselves 6 to what power equals 31? I don't know what that equals. I mean, I can estimate 6 to the first is 6. 6 squared is 36. So I know it's got to be 1 point something. But we can use the change of base formula to say that this is the log base 10 of 31 divided by the log base 10 of 6. Now, I don't happen to know either one of those values, but luckily for us, our calculator has the common log function. We can throw that into our calculator and see that it's roughly 1.9. Our authors will tell us we should go ahead and figure out what the log of 31 and the log of 6 is and then divide, but you can just jump right to your calculator and type that in. Also, please note that choosing the common log is great. We could just as easily choose the natural log. But even though the common and the natural logs in this situation is interchangeable, we have to be consistent. If we have the common log in the numerator, it must be the common log in the denominator. Don't flip-flop them and simply say, oh, I can use any one at any time and have the natural log divided by the common log or something like that. Example 5 is just the same as example 4. What's the log base 9 of 44? They're now asking us to use natural logs, and so we can use the change of base formula to say that that is equal to the log base e of 44 divided by the log base e of 9. More simply expressed, the natural log of 44 divided by the natural log of 9. Check out what those values equal and perform the division, or just type in natural log of 44, close parentheses, divided by the natural log of 9, see if you don't come out to the same value of about 1.7223. Same discussion as before. If you wanted to use the common log divided by the common log, you should come to the exact same result. And we can finish up today's lesson with a word problem. For a sound with intensity I, the loudness L of I of the sound in decibels is given by this function. L of I is equal to 10 times the log of I divided by I sub 0, where I sub 0 is the intensity of a barely audible sound. An artist in a recording studio turns up the volume of a track so that the intensity of the sound doubles. By how many decibels does the loudness increase? So we can think about what we're talking about. If the loudness is based upon this formula and the intensity is doubling, then where we see I, we would want to write 2I. Okay, so we're going to talk about the loudness of double the intensity minus the loudness of the original intensity in order to see what the difference is between the two. So take a look at that simple expression L of 2I minus L of I and look above to what the original function is. How can we rewrite this? We'll perform a substitution. We're basically subtracting the same two things. It's just that that 2I, appears in the numerator of the first expression. Okay, now when we look at this, they're very similar. They're almost identical to one another. If we want to simplify this expression, a really good thing to do would be to factor out those 10s. The distributive property tells us that we could take 10 times both of those expressions and get back to the original. Factoring out is just another way to describe the distributive property, basically in reverse. Now within the set of parentheses, they're almost identical. The 2 is the only difference, and it's 2 times I. So remember, when we have a product within the log, we can expand that through the product property, and so that first expression in the set of parentheses can be expanded out so that it's the log of 2 plus the log of I divided by I sub 0. Notice also that the third expression there is identical to the second. So let's simplify. Let's just simply subtract those two, and we're left with 10 times the log of 2. Grab your calculator and throw that in. What is 10 times the log of 2? It's about 3.0103. And so the loudness increases by about 3 decibels when we double the sound, the intensity of the sound. So please don't leave today without feeling comfortable about these 3 properties in one formula. When we have the product property, we can expand through addition. When we have the quotient property, we can expand through subtraction. When we have the power property, we can take that exponent of 6 and it can come out as a coefficient. And let's just pause here to say that the up arrows work also. If 6 is a coefficient, we can bring that up as an exponent. And if we have multiple log expressions with the same base and they're separated by either addition or subtraction, we can bring them together using the product or quotient properties. We can condense into single logs. And finally, that change of base formula, we can set that out to being the log base b of 36 in this particular example, divided by the log base b of 4. Use whatever b seems most logical to you. In most cases, that will either be 10 or e, but please just make sure that you're consistent. Those b's have to be the same. Thank you so much for watching. Your homework will be posted, and have a great day.